Greetings and welcome to Chapter 1, Section 5 in Calculus 1. In this section, we're going to talk about inverse functions and logarithms, and I'm going to use a homework assignment that I've created in WebAssign in conjunction with James Stewart's Calculus 8th edition Early Transcendentals. And in this video, I'm going to use pretty much the same format as I did in previous videos for my Calc 1 series and go through this homework assignment and make some comments on some of these problems. For my own students, I'll be helping you get started on some of the problems, and on other problems I will work them all the way through, and since they're algorithmic, you'll have to do some of your own calculations when you're working your own problems. I will also be toggling back and forth between, not a lot, but every once in a while, between these problems and James Stewart's ebook in order to encourage you to be going and finding your own answers and doing your own investigation and finding problems that are similar to the ones that we're looking at so that you can work through them on your own. Also going over and looking for a couple of definitions and things like that. What else did I want to tell you? Also, I'm going to do my best for the past couple and for this and for previous videos, making sure to put some timestamps in the notes. So please look for those if you're trying to jump to a particular topic. I'll do my best to give some accurate but short descriptions of what I'm doing as I'm going through these videos. And so without further ado, let's have a look at problem number 1. So this first question is asking us about a one-to-one function, and you could definitely just jump on the web and search what is a one-to-one function. You could without a doubt dip into your ebook and find out what a one-to-one function is. And the short version of the story is that a one-to-one function can be tested for, if you're looking at a graph, you can test to tell if the function that you're looking at graphically is a one-to-one function by using the horizontal line test. And the horizontal line test works exactly the same way as the vertical line test does, except you're using a horizontal line. So just maybe a quick example would be, let's just draw some really rough sketches. And if I have a parabola, maybe an upside down parabola, would this be the graph of a function? Definitely, because it passes the vertical line test. Is this an example of a one-to-one function? The answer is no, because it's possible to draw a horizontal line that crosses the graph at more than one point. So where the vertical line test is checking to see if you have repeated x values, here we're looking to see if we have repeated y values. And it's pretty clear that this point and this point share the same y value. Why does that tell us that it's not a one-to-one function? How does that come into play? You probably looked at this pretty closely in a pre-calc or a trig class when you were looking at restricted domains of trig functions, and then you started learning about inverse trig functions. The graph of this function, a parabola, or even if we looked at the more basic parabola like y equals x squared, you know that that graph looks like this. The graph of the inverse of this function really should look like this. How can you generate the graph of an inverse function? Or how can you generate the graph of the inverse of a function? Visually, graphically, you can take your initial graph and reflect it over the line y equals x. And the red and green graphs here are reflections of each other over the line y equals x that I just drew, that diagonal line through the first and third quadrants. The problem is that the graph of the inverse, the green sideways facing parabola, is clearly not the graph of a function. So again, what's a one-to-one function? A one-to-one function is a function that has an inverse that is also a function. So y equals x squared is not a one-to-one function. How can you tell the graph is a function, whether it's one-to-one? Using the horizontal line test. What is a one-to-one function? I'm going to let you read through those multiple choice options and choose the best one. But graphically, inverse functions are reflections of each other over the line y equals x, and a function is a one-to-one function if its inverse is also a function. A one-to-one function is a function that passes the horizontal line test. I think that'll take you through problem number 1 there. Problem 2 says a function is given by a graph, determine whether it's one-to-one. Now that we've talked about how you can test to see if a function is one-to-one, I think you can answer this one no problem. The given graph is clearly a function because it passes the vertical line test. The question is its inverse going to be a function? Assume that f is a one-to-one function. Okay, we're making that assumption. If f of 8 is 18, what is f inverse of 8? Let me remind you that if we have a domain and we have a range and a value such as 8 in our domain maps to 18 in the range, so this x value has a corresponding y value of 18, we can arrive to the number 18 by taking the number 8 and plugging it into our function, in this case called f. How could I get from the 18 back to the number 8? And the answer is you take the number 18 and you plug it into the inverse function. It looks like f to the negative first power. We say f inverse. So here, so far, it looks like for each x value in the domain, there is one and only one y value in the range, and for each y value in the range, it maps back to only one domain value. What would this look like if the function were not a one-to-one function? It's possible, especially in the case of a parabola, that maybe the number 10 also maps to the number 18. If that were the case, and then I tried to go from 18 in the range back over to the domain, f inverse of 18, as I try to map again from the range back to the domain, this equals two different values. This would equal 8 or 10. One input value, two output values, not a function. So f inverse, if I ask you, is f inverse a function? The answer would be no, because 18 maps back to the 8 or the 10. Visually, graphically, if you tried to graph that with an input value of 18, you'd have an output value of 8 or 10, which would not pass the vertical line test. And I'm talking about examining f inverse here. However, we were told that f is a one-to-one function, so we don't have to worry about any kind of original duplicate use of the number 8 mapping over to 18, so f inverse is going to map back to the number 8. That same idea applies to part B. The original function takes you from domain to range. the inverse function takes you from range to domain. So even though part B is starting out with an F inverse statement and then asking you about the original function, you can answer the same, you can answer part B using the same rationale and the same kind of a mapping diagram. Number 4 asks us to find a formula for the inverse function. So now we're not being given a graph, we're not being given a mapping, we're trying to actually find the inverse function. And there's a very straightforward process that we can use. What I like to do is to rewrite the given function. Instead of using function notation, I rewrite it as y equals. Then I take the x and the y and I literally have them trade places as though they've stood up and walked over and sat down in each other's chairs. So I would rewrite this as x equals 2 plus the square root of 4 plus 5y. So you can see that they've traded places. I'm also being very organized. I'm trying to keep things lined up and do one thing at a time so we see what changes as we go from line to line. And I will typically do that in all of my videos. Trying to help keep you organized, keeps me organized. And if you want to put a little note over here, which I like to do, maybe say swap x and y. So that's what we did in order to get from the first line to the second line. Now the next group of steps is going to help us solve for y. We're going to isolate y on the right-hand side of the equation. So let's subtract 2 from both sides. And then we will square both sides. So I'll put a little caret with a 2. So I'm raising both sides to the power of 2. On the left-hand side, I'm going to do x minus 2 times x minus 2, FOIL and combine like terms. The result of that is x squared minus 4x plus 4. On the right-hand side, squaring a square root leaves us with 4 plus 5y. Then I will subtract 4 from both sides. And lastly, divide both sides by 5. You know how to do all of those things, which is great. So we've done it, we've isolated y. And actually what we have here is the inverse function. My last step is going to be replacing y with f inverse. So that's what your inverse function looks like. And I'm going to go back and put in one additional note, which would be good for you to have in your notes. And that is that we took these steps in order to solve for y. So those individual steps will vary from problem to problem, but as a whole, that's what we were trying to achieve there. Once we had the y isolated, we replaced it with f inverse. So you could put that in here, replace y with f inverse if you want, and you got yourself a final answer. It doesn't matter what this original function is, and in fact, in problem number 5, we're being given a different function and asked to find a formula for the inverse function. We're going to take these exact same steps. And when I say these exact same steps, I mean this step, and this step, and this step. Those three things will be the same. However, these steps are going to be different. Let's check it out. I'm just down here getting my pens organized. There we go. Okay. Oops. Find a formula for the inverse function. Step number 1. Rewrite as a y equals. Swap x and y. Did that, okay, and now we're going to go through the motions of solving for y. So let's add 7 to both sides. X plus 7 equals e to the 5y. Now we run into the problem here that we've seen in previous problems, in previous videos, where our variable is up in the exponent position. How do we bring it down onto the ground, as I like to say? And the answer is we're going to take the natural log of both sides. Sometimes taking the natural log is really convenient, as it is here, because the natural log and the e to the power of essentially cancel each other out, leaving us just with the 5y on the right-hand side of the equation. I'm going to take a minute to remind you of why it is that the natural log and the e cancel each other out. So all I've done is written the natural log into the left-hand and right-hand sides of this equation. The natural log and the e on the right-hand side are going to cancel each other out because the power rule for logarithms tells us that we can take the 5y and write it in front of the natural log like it's a coefficient. The next thing we can do is we can actually evaluate the natural log of e. The natural log, remember, is a logarithm with an implied base of e. So what the natural log of e is really asking us is e to what power equals e? And the answer is 1. E to the first power equals 1. So really, this expression is equivalent to 1. So the e and the natural log aren't really canceling out so much as they evaluate to a multiple of 1, which we don't really need to include because a multiple of 1 doesn't do anything. So this would finally leave us just with 5y. So on the next line, I'll rewrite the natural log on the left-hand side. And simplifying the right-hand side, we have just a 5y. We can now divide both sides by 5. And then we can do that very last step, which is really this is our final answer, except we're going to change the y to say f inverse of x, and that'll be our final answer. I'll leave you to copy that down in your notes. Problem number 6 gives us the graph of a function f and asks us to sketch the graph of the inverse. I mentioned in problem number 1 that the graph of a function and the graph of its inverse are reflections over the line y equals x. So I say that in a very specific way. The graph of a function and its inverse. I didn't say the graph of a function and its inverse function, because it's not always going to be the case that the graph of a function is going to have an inverse which has a graph that's also a function. And we saw that in problem number 1. I took a parabola and then I graphed its inverse, and its inverse was a sideways facing parabola, which fails the vertical line test, which means it's not a function. So a function will have an inverse. You can always graph the inverse, but that inverse won't always be a function. So here, before I started the video, I just came down here and drew a quick little sketch of a sort of a sample graph so that we're not working out the graph that is actually problem number 6. And as far as a technique for graphing an inverse function when you're given the original function, because the domain and the range have this one-to-one relationship when you're working with an inverse function, the domain maps to the range, and then the inverse function maps from the range effectively back to the domain. It's as though the x and y values are trading places, and in fact they are. So if I pick a point on this red curve that I've drawn, that point has x and y coordinates. If I were to take and swap those x and y coordinates, now this is a hand-drawn graph, so bear with me. 1, 2, 3, 4. 1, 2, 3. So let's say that this point right here has coordinates 4, 3. When I take that point and I reflect it over this gray line, which is y equals x, the coordinates of the new point will be 3, 4. Literally, the coordinates are trading places. So let me go over 3 and up 4, and I'll arrive. See, this is the problem with a hand-drawn graph, is it's not going to work out as nicely as it's supposed to. But that's the idea. Our new point will be graphed at 4, 3. Or sorry, 3, 4. I'm going to erase these now. So without putting any little markers on the axes, another way that you can think of what's happening visually, graphically, is that if I take this point that I've drawn here and I move, I need a different color. Let's see. This should be pretty visible. If I move perpendicular to the x, or to the line y equals x, and then I travel that same distance crossing over the line y equals x, I will arrive at the point which appears on my inverse function. This is the process of reflecting a graph over the line y equals x. I can do the same thing with this point down here. Let's take this point that's on the negative x-axis and let's reflect it over the line y equals x. So we'll come over here, perpendicular to the line y equals x, and then we'll travel that same distance through, and we will end up at our new point. It shouldn't be a surprise that a line or a point that started on the negative x-axis, when you reflect it over the line y equals x, it ends up on the negative y-axis because our x's and y's are trading places. Let's apply that to a better looking graph than the one that I was just drawing. For example, let's take, where's a good one? Let's look at this point up here. This point is about 2.5, 3. 2.5, 3. Which means that the point on the inverse graph should be 3, 2.5. So let me go over 3 and up 2.5. This writing is going to be in my way. Let's see, the first point that I just marked there was at 2.5, 3. The new point will be at 3, 2.5. So I'm coming over 3, going up 2.5. So when I reflect my graph over the line y equals x, I should end up with this point at 3, 2.5. Is it really going to work? Can we test it better on this graph than on previous ones? I think so. Let me switch over to a black pen and we'll make it a light line. And I'm actually using a straight edge on my iPad, and I'm going to sketch in the line y equals x. There we go. I'll label it. And does it look like these 2 points have been reflected over the line y equals x? Yes. Now that we're working on a proper graph, we can see pretty clearly that that's the case. So if you go through and grab a couple of convenient points that have sort of nice numbers for coordinates, and you reverse those coordinates and you plot those new points, it should help you, especially in a multiple choice situation, select from the correct graph, or if you had to be graphing by hand. Really nice that in this problem, these are straight lines. It would be easy for you to construct the graph of the inverse. So here we want to find the exact value of each expression. And just a good little quick review of logarithms. Remember that if you have a log with a base of b being applied to m, and if the result of that log is n, this equation, or this statement, is equivalent to this one that says b, which is the base, raised to the power of n is equal to m. So you can use those interchangeably. What it means is, or another way to look at it is this, especially as pertains to the questions that we're being asked over here in this problem. If we match that up to this, what it means is that b to some power equals m. And the way that I've diagrammed it here, the answer to that question would be n. B to some power equals m. The base to some power equals m. Maybe you call that the argument. And b is the base. If we apply that line of questioning to problem A, the question is 2 to what power equals 16? I think you can answer that on your own. Part B, what this logarithm is really asking us, again, applying that same thought process, is 64 to what power equals 2? You should be able to figure that out. You might even know it off the top of your head. 64 to what power equals 2? I'll give you a hint, at least I think it's a hint. 64 is 2 to the 6th power. You have to take 64, 2 to the 6th power, and raise it to another power so that your answer is 2 to the 1st power. So again, the 64s are here, and that's this 64, and then the 2 is this 2, and you've got to figure out what the question mark is, what the answer is. I will leave that to you. And move on to question 8. Solve each equation for x. This is very similar to a problem that we've already done. We have the variable in the exponent position. In order to bring it down onto the ground, my recommendation is taking the natural log of both sides. The natural log and the e are going to cancel each other out, so to speak, and from there it's just arithmetic. So in this video, look back a few problems, find the problem where we were finding inverse functions, and do your best to solve for x. Part B is a little different. This is, again, a topic that's probably covered in a college algebra class. The idea of solving for x in part A required us to take the natural log of both sides. Here, that variable in part B is not trapped in the exponent position, it's trapped on the inside of a natural log. If only I knew something that sort of canceled out with a natural log. Well, in part A, you used natural log to cancel out the e. In part B, we're going to use e to cancel out the natural log. So let's see how that frames up. I'm going to make the left side and the right-hand side of this equation exponents. I think it's safe to say, while that might sound magical and I made it sound very dramatic, I think it's safe to say that 2 to the power of, if 2 to the power of m equals 2 to the power of n, then m and n must be the same value. That same thought process is what we're going to use, but in reverse. If I tell you that m is equal to n, then surely 2 to the m equals 2 to the n. So in this case, this is m, and this is n. So let's make them into exponents. Will we use a 2 under them? We will not. We're going to use e. E to the natural log of 3x minus 18 equals e to the 8. Why did we do that? Because e or e to the power of and natural log are inverse functions, just like, or much like, squaring and square rooting. They kind of cancel each other out. Here the e and the natural log are going to cancel each other out, leaving us just with a 3x minus 18 on the left-hand side. You've got e to the 8th power, which is a non-terminating, non-repeating decimal, like pi, e to the 8. You need to add 18 to both sides, divide both sides by 3, and get yourself a final answer for x. When you write your final answer, I would say leave it just like that. I wouldn't do any rounding. I don't see any instructions here that say round, so if you're supposed to give an exact answer, let's take it all the way. If we add 18 to both sides, I think that you're typing this in as a final answer. The farther you go into math, I've found the higher the likelihood that you're going to end up with an answer that's really gnarly looking. And the farther you go, the more likely it is that you're going to be asked for an exact answer. Now, in an applied problem, nobody's going to want some really long decimal number of inches or pounds or tons or miles or anything like that. But in a sort of purely mathematical question, like we have in part B, this is going to be your exact answer. Number 9, we are moving into a word problem or an applied problem. Let's get the whole thing on the screen here. It's a long question. So we have a bacteria population starting with 60. It doubles every 2 hours. And we're being given a formula for the number of bacteria after t hours. And we're being told that that number of bacteria is represented using n. Or f of t. And we want to find the inverse of that function. I think we've talked enough about finding inverses, so maybe I'll tell you to, why don't you start it off by writing that n is equal to 60 times 2 to the power of t over 2. Then use your 3 primary steps. Swap your variables, solve for n in this case. You will need to use natural log. It's not going to cancel, natural log and the 2 are not going to cancel each other out. Natural log and e cancel each other out, but you'll still use the natural log. You'll still use the power rule for logarithms to bring your exponent out in front of the natural log. We did that in a previous problem in this video, so you can look back to it if you need to. Bring that exponent down onto the ground in front of the natural log. Dividing both sides by a natural log is okay. You can divide both sides by a natural log of 2, and you'll need to do that. And just keep chipping away at it, go slowly, and solve for you'll be solving for n, and that is going to be your inverse function. Explain the meaning. This we can talk about without having found the inverse function. What the original function does, what f of t does, is we put in an amount of time and it gives us out a number of bacteria. So the domain is time values and the range is number of bacteria, which is represented by n. So our original function is mapping in this way, which means our inverse function is mapping in this way. F to the negative first power, f inverse. So this function, f inverse of n, this function tells us how long it will take to obtain n bacteria, given the number t. Given the number t, it doesn't look like that's what we're plugging in there. So read through these two statements, make sure that you're deciding on the correct one. And then the question of when will the population reach 10,000? In the original function, which is right up underneath me there, the value that we're plugging in is time. In the inverse function, which you just calculated, the input value is a number of bacteria. A number like 10,000. So you're going to have to take the 10,000, plug it into the inverse function that you've designed, and figure out an amount of time that answers the question, when will the population reach 10,000, or whatever value you're working with. And this time we do want to round our answer to 1 decimal place. And remember, you're working with hours. You don't have to type in hours because this text entry box already has the HR for you. Just realize that that number that you're finally getting there does have units associated with it. In problem number 10, this is a throwback to a pre-calc or trig class. We're being asked for the inverse cosine of -1. The cosine function, this is a nice question. This ties in with a lot of what we're doing in this video. The cosine function goes like this. To the best of my hand-drawn ability, it's embarrassing. It didn't look so bad when I was looking at it when I was writing it, but now that I'm looking up at the screen, it's humbling. The cosine curve goes forever to the left and to the right. And if we were to take this graph and reflect it over the line y equals x, what we would end up with is a graph that looks, this is not remotely correct, but it's going to look something like this. Now, is that orange graph that I just drew the graph of a function? Definitely not. It does not pass the vertical line test. From looking at the original graph of the cosine function, is the cosine function 1-to-1? Think about it. Is the original cosine function 1-to-1? How do you test to see if a function is a 1-to-1 function? You ask yourself, does it pass which test? The horizontal line test. Does this graph that I drew pass the horizontal line test? Big time, no. Over and over and over again, for infinity, it fails the horizontal line test. It passes the vertical line test, it's a function, but its inverse is not going to be a function. So what we learned in in a pre-calc class is that we can make the cosine function into a one-to-one function if we restrict the domain. And what that means is that we're going to remove a lot of the original cosine graph, and we're only going to use this part of it. The part of the cosine graph which I've just drawn over with my orange pen, is it a function? Passes the vertical line test. Is it a one-to-one function? Does it pass the horizontal line test? Well, now it does. So if we restrict the domain of the cosine function, then it becomes a one-to-one function, and so we can have a conversation about its inverse, which is also a function now, but with these restricted input values. The range of the cosine function goes from negative 1 to 1, including negative 1 and 1. The restricted domain of the cosine function goes from 0 to pi, inclusive. So that's for the cosine function. When we're talking about the inverse cosine function, this becomes the domain and this becomes the range. And remember that you could graph the inverse cosine function by taking what I have in orange on this graph and reflecting it over the line y equals x, which you can do by swapping x and y coordinates, effectively taking the domain and the range, which I wrote incorrectly there for a moment, taking the domain and range and having them trade places, which is what I've done. In purple, I've got them as domain and range. In orange, I have them as range and domain. I had them trade places. Okay. Does that help me answer this question? For me, it does. Because what I'm doing in question part A is I have the inverse cosine of negative 1. So I'm using negative 1 as an input value into the inverse cosine function, which means I'm taking a negative 1 as a domain value, an input value for the inverse cosine function. The question is, what then does it map to in the range for the inverse cosine function? Well, because this is a one-to-one function, it's going to map to the same range value that would normally have been a domain value mapping over here to the number negative 1. So we're literally going full circle. Negative 1 for inverse cosine is mapping over to the range, which is the domain, which is going to map back over here to the range, which is that same value of negative 1, which would take us down to here, and then it almost looks like a circle. So when I see this question, I ask myself, the cosine of what value would equal negative 1? Once I determine that the question is actually answerable, then I reframe the question in my mind like this. And in order to answer that question, you could draw triangles and make sure that you're putting them in the correct quadrants. You can talk about adjacent divided by hypotenuse and how is that going to end up giving me an answer of -1. All of those are very valid ways to answer this question. I also encourage you to use this graph. This is the graph of the cosine function, which is good because what I'm circling here is the cosine function. I'm looking for an input value that gives me an output value or a y value of -1. Look over at this graph with me. Where on this restricted domain graph do you see a point that has a y coordinate of -1? I think it's right there. And what's the x value that goes along with that y value at that point? And the answer is pi. And so the inverse cosine of -1 is pi. That was a fairly comprehensive review of the trig function cosine, the inverse trig function, or the inverse of the cosine function, the fact that we need a restricted domain on cosine so that the inverse cosine is actually a function. So restricting the domain allowed it to be a one-to-one function. We looked at the mapping of the domain and the range of the cosine function and the inverse cosine function, and talked a little bit about the relationship of how an input value, which normally has an output value, that output value becomes an input value when you start looking at the inverse function, because inputs and outputs, domains and ranges trade places. I'm going to let you go through that entire thought process again with the inverse sine function. It's a good chance for you to refresh your memory on the graphs of those trig functions, and we will be, in a very calculus sort of fashion, we will be working with those trig functions again. And some of you are going to have professors and instructors who want you to be memorizing many of those relationships. I personally request or require my students to know the graphs of those functions and the various quadrants and so on in a lot more visual way than a lot of professors do. So just make sure that you're preparing yourself and being sensitive to the requests of your instructor. We talked about evaluating logarithms already like this. The second problem that we saw in an earlier question did involve something like this, and the number 64, as I recall. Remember that this is asking you 3 to what power equals 1 over 27. Maybe a hint is that the number 27 is 3 to the third. So now you've got 1 over 3 to the third. Is there any other way that you could write this so that the 3 to the third was not in the denominator? Contemplate that. It might help you. And question number 12. You in an algebra class have definitely worked with expanding and, I don't know what the opposite of expanding is, compressing maybe? Logarithms, when you were studying properties of logarithms. Find the exact value of each expression. We don't want to evaluate this, and evaluate this, and evaluate this, and then try to do arithmetic with subtraction and addition. Don't do it. It won't be pretty. Instead, use your properties of logarithms. Here, because there's a positive 1 in front of this logarithm, I'm going to rewrite a new logarithm that says the log base 3 of, and because this logarithm was positive, I'm going to take the 12 and put it into a numerator inside of this new logarithm. And in the second term, because it has a negative coefficient, I'm going to put the 28 into the denominator. So now I'm doing, let's see. Terrible, 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 terrible. I see the 12 here, I see the minus sign here, and the 28 here. Instead of doing minus, as I'm combining these logarithms, that subtraction sort of, in a way, turns into division, which is why I have this division line right here. The addition symbol that you're seeing here is going to, in a way, turn into multiplication. And because it's positive, that multiplication is happening into the numerator again. If it's positive, it ends up in the numerator. If it's negative, it ends up in the denominator. If it's possible to simplify this, we will. 12 and 28 certainly reduce by a factor of 2. In fact, they reduce by a factor of 4. And then if there's any final reducing that you can do this way, you'll do that. And then once you have this entire argument simplified as possible, you will try to evaluate this logarithm. And if 3 to a power ends up equaling this argument, then the exponent will be your answer, just as it was in the two previous problems. 3 to what power equaled 81? 3 to what power equaled 1 over 27? This problem is 3 to what power equals whatever this turns out to be. I'm going to leave it up to you to figure that out. And in part B, you're going to go through the same process. This is positive, so the 150 ends up in the numerator. This is negative, so the 75 goes in the denominator. This is negative, so the 50 multiplies into the denominator. Simplify the argument, and then ask yourself 5 to what power equals that argument. In number 13, express the given quantity as a single logarithm. This is giving us the chance to use the reverse power rule for logarithms, which says that a coefficient can now be placed back up here as an exponent. So we could write this as the natural log of 3 plus the natural log of 4 to the power of 2, which of course is 16. And then addition is the same thing as multiplication, so you're going to have the natural log of 3 times 16. You multiply 3 by 16, and then I want you to realize that e to what power equals this number. That's not a number you want to write out. That's a decimal, it's nasty, so you're simply going to write your final answer as the natural log of whatever that argument turns out to be. That's considered an exact answer. In number 14, this is a lot of trig review in this section. In number 14, we're taking the tan of the arctan. Arctan is synonymous with inverse tan. We could have written that as tan to the negative 1, which is how we write inverse tan. And is it correct that tangent and inverse tan cancel each other out, just like natural log and e, or squaring and square rooting? Each one of these trig functions needs to be considered carefully and sort of on their own. Tan and arctan will cancel each other out as long as this number, the 6 in this case, is in the restricted domain of the arctan function. And I say restricted domain because it's part of that conversation like we had much earlier about inverse cosine, and I drew the graph and then I erased part of the graph and we only worked with it from 0 to pi and negative 1 to 1. Same kind of a topic here. That's I was restricting the domain of the cosine. Here we would have to restrict the domain of tangent, reflect it over the line y equals x in order to get arctan, and so on. So does 6 end up in the restricted domain for arctan? Just as a quick reminder, the tangent function, one period of the tangent function, looks like this. It appears again over here and 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 over here forever in both directions, right, including the asymptotes. But let's just look at this one period that's in the middle. The domain goes from negative pi over 2 to pi over 2. Those are asymptotes, so the domain would have parentheses on it because we're excluding those values. And the inverse tan, when we reflect this over the line y equals x, we get a graph that looks a lot like this, and the horizontal asymptotes, or the vertical asymptotes, come with us and become horizontal asymptotes. Those orange asymptotes are supposed to be horizontal. They look a little angled. And so, looking at this orange graph that I've drawn, as rough as it is, does the number 6 look like it's in the domain of that orange graph? Is there a point on this orange curve that has an x-coordinate of 6? I would say yes. In fact, it looks like that arctan graph goes forever to the right and forever to the left. I think that the domain of the arctan function goes from negative to positive infinity. Okay. Well, since that's the case, since 6 is in the domain of the arctan function, then the arctan and the tan are going to cancel each other out, and your final answer is just going to be 6. Things get more complicated when we get to part B, because the sine function, when we restrict the domain, looks like this. It also goes from, let's see, this goes from negative pi over 2 to pi over 2. And let's actually write those down. I'm trying to write them down anyway. For sine, the domain goes from negative pi over 2 to pi over 2. That's the domain of the restricted sine function. Is 7 pi over 3 in that domain? I don't think 7 pi over 3 is in there. 7 pi over 3 is larger than 2 pi for that matter. What we might want to consider doing, or what we should definitely consider exploring, is the possibility that since the period of the sine function is 7 pi over 3, the sine of 7 pi over 3 is therefore equivalent to the sine of 7 pi over 3 minus 2 pi, which is equal to the sine of pi over 3. Is pi over 3 in the domain of the restricted sine function, or the restricted domain of the restricted sine function? Pi over 3 is definitely between negative pi over 2 and pi over 2. Since 7 pi over 3 is equivalent to the sine of pi over 3, excuse me, I'm going to rewrite the original question as the inverse sine of the sine of pi over 3. And as we talked about in the previous problem, since pi over 3 is in the domain of the restricted sine function, and therefore in the range of the, well, it doesn't matter if it's in the range. We're just checking the domain of the inner function. And if you look back at the original question right here, to the right of my head, this is the inner function. I'm concerned with the domain of the restricted sine function, since sine is the inner function. Originally, the argument 7 pi over 3 was not in the domain of the restricted sine function. However, we were able to use some properties of the sine function to manipulate that original statement into a statement where we're now looking at the sine of pi over 3. We ask ourselves again, does the argument pi over 3, is that pi over 3 in the domain of the restricted inner function, the sine function? The answer is yes. Therefore, now the inverse sine and the sine will cancel each other out, leaving us with a final answer of pi over 3. So not 7 pi over 3, but pi over 3. And that was quite the review. I'm going to go create some timestamps. I hope that that was helpful for you, and I hope to see you in the next section. Thanks so much.